software reactor in Redmond. Those of you joining us online, you'll be seeing the code of conduct. This is the code of conduct that we follow here at any of the Microsoft events. Specifically, we don't tolerate any discrimination or harassment. This evening, we're going to have Ben talk to us. And whenever you are ready.
All right. I think, but this is the presentation on the technology of AI art. So this is a very, very cutting edge and sort of space, even though it's been going on for quite a while, and it's based on the mathematical work that's been done since 2015 or so. The sort of big explosion happened just recently with DALL-E 2, and then subsequently Imagen, and then subsequently Stable Diffusion, which is what we're going to focus on today. It's very kind of exciting the way that AI art has progressed from something that essentially generated extremely poor quality and images with some very questionable kind of arrangements to something that really produces very high quality results that could even compete with regular artists in some senses. And so let us dive right into it. So who am I? So my name is Benjamin Sobel. I work as a software engineer at a company called Mosaic ATM, and we do work on drone imaging and on machine learning regarding drones and the footage that gets sent back from them. But as an aside, I also draw artwork like the little self-portrait there that you see in my spare time. So I think that makes me very well fitted to discuss the AI art and this kind of general brand new space. So this is for, who is this for? This is for anyone who's interested in the internals and structure and the way that all of these new diffusion models were trained and how this sort of breakthrough occurred, as well as anyone interested in the general cutting edge of the field, and just anyone who's enthusiastic about this sort of brand new space. Disclaimer, mathematics. So there are a lot of interesting mathematics and probability that are going on in here. But I will be refraining from going too deeply into them in order to keep the focus of this presentation a little bit broad, and in order to avoid creating a lot of confusion and a lot of very specific sorts of discussions that can result from that. So in general, we're going to discuss the implementation and the kind of broad theory and strategies that go into the creation of these models. But I do have the mathematics, obviously, and links to discussions about that in the credits of this slideshow if you're interested. So let's go through a few introductory terms just to make sure that the rest of the slide is, the rest of the presentation is clear. So just in case anyone is confused, we're going to be talking about information, entropy, neural networks, and text encoder. So what is information? So in this context, in terms of information theory, information is essentially the what we want, the kind of subject that we are, the core element of what we are focusing on within a particular piece of data. So in the example on the right, I have this kind of hard to predict, kind of highly noisy information, and then a very clear set of information that's just the letter A repeated over and over and over again. So the letter A repeated over and over and over again, it has a lot of, it doesn't have a lot of information in it because we can replace it essentially with just the sentence, the letter A repeated 500 times, is it pretty much. So this kind of model of information is important to understand how and why we focus on certain things, and we focus on within kind of this sphere. So entropy, as I briefly touched on previously, is the opposite of information. It's kind of noise or heat or kind of non-predictive elements that we aren't focusing on. And so compression and decompression are how we remove or return entropy to an item. So if you think of a zip file, if you take a text file of all the works of Shakespeare or something, and you run it through zip, 7-zip or something, you'll result in a very much smaller file, and then you can unzip it back to its full size. So in a sense, but what it's doing, what is happening when that file gets zipped, is that it's removing all of the unnecessary entropy and then putting it back in when it has to be unzipped. So it's getting crushed down, and then it's getting expanded back again. And then a vector, I assume a lot of people will know this, but vector is very important to mathematics. But in this context, we're just going to refer. We just mean a set of numbers with a fixed size that we're operating on with the neural network or with various things. And this is an image that I created by asking Stable Diffusion to describe a vector. So just a short little example of that. And then neural networks. Obviously, neural networks are very simple or very well understood at this point, but they are essentially trained kind of sets of vectors that we teach using backpropagation to go from a set of inputs to a set of outputs and back and forth, possibly. Now, and then a text encoder, which will become important later, is just an encoder that takes natural language, like the language that we're speaking, which has a lot of entropy, and crushes it down into a vector that we can use as input to these models. So what is Stable Diffusion? Let's finally come to the main subject of what we are going to be discussing. So Stable Diffusion is a latent diffusion model that was just recently released. It's become much more popular than many of the other models like Midjourney, Imogen, and DALL-E 2 because it's open source and because anyone can use it. So it's become, in many ways, the main diffusion model that a lot of people are working on. And there's a lot of tools out there that have been designed for it. And this is a little image that I generated with Stable Diffusion. It wasn't designed or drawn by any other artist, just a pure kind of product of the machine, which I thought was very cool. So what's in the name Stable Diffusion? So the name comes from what type of algorithm it is. It's a diffusion model. In this context, diffusion is kind of analogous with heat or with noise. It's melting away the original kind of informational features of the image to just a flat, noisy plane. And so it's it does this in order to kind of reverse that process later. And we'll see how that works. So latent diffusion in the context of Stable Diffusion is something we'll get into a bit later, but it essentially means that it's operating on a hidden variable that is rather than the variables that we're all working with. So diffusion models are just the most recent in a broader category of attempts to generate images, or generate high-quality images and operate on high-quality images within neural networks. So there have been the GANs, or generative adversarial networks, that basically have a network that tries to generate an image or a piece of text or something, and then an kind of an adversary network that tries to discriminate whether or not that was a correct or valid generation. So for example, if you've ever seen the website, "This person does not exist," that was generated using GANs. But GANs have a lot of problems. They are very, very hard to train. The score function is hard to kind of get working. And they are very, very costly as far as the amount of compute resources that are required. Then there are also the VAEs, the variational autoencoders. And these are actually come in handy later, but they essentially they crush down the data down to a smaller kind of latent space vector representation of it, and then they try to expand that back to the uncompressed or original image. And this allows them to be trained very, very easily because there's, I mean, all you need is just an image. You don't even need anything else. And it greatly expands their abilities in a sense, but it also costs, I mean, it doesn't really produce very much as far as the most powerful possible sort of methods of image modification go. There's flow-based models, which we won't be getting into very much. And then finally, we come to diffusion models, which is the brand new and exciting one. So the variational autoencoder, as I was discussed, is going to come in important later, but it's essentially crushing down the information and then expanding it back. So it's crushing it down to a version that has much less entropy than the natural images tend to have. And it's expanding it back to the original version, which has all of the entropy. So diffusion models, they work by learning step by step to go from a noisier image to a less noisy image while using only the information of the original image and the conditioner or the language vector that they are being given, in a sense, in this context. So there are two main types that have become very, very popular, although there's also score-based diffusion models, but not very many of the major diffusion models use that framework. So we'll mostly be talking about the two here, and mostly about the latter one, the cascade diffusion and latent diffusion. So diffusion models, all of them, both cascade and latent, they operate on the principle of denoising, in a sense. So they take a completely, a very noisy sort of image, and they are trained to essentially remove all of that noise and restore the original image. And when you add in the factor of the additional factor of the language conditioner, you can use this to go essentially from a completely noisy image back to the original image, in a sense. And they do this step by step. So each step kind of only removes a very small amount of the noise, in a sense, until you get the resulting image. So this is an example of what the inputs, obviously these aren't the actual inputs, since there's other more complicated things that that have to be done for the cascade and latent diffusion models. But for a naive implementation, basically, of the diffusion process, we would set up images like these, and we would train the neural network on a series of inputs, with the inputs being each of these noisier images, and then the outputs being the next least noisy image. So in other words, it's going from this image to that one, 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 to that one. And with each kind of associated image, it has the language model or the language vector associated with it that conditions it to transform. For example, if the label for this image was a dog in a grassy field, it would have each training pair would receive as inputs the noisy image a language vector representing a dog in a grassy field, and then it would be trained on the output of the slightly less noisy image. Yes? So in the so essentially, like all of these images are used essentially as part of the training process. I was trying not to go too much into the mathematics and focus more on the theory, but in the actual training, what you do is it also receives as input the which step is located at, so that it knows kind of how much information to restore, basically, and other things like that. There's a little bit more that goes into it. This is just the kind of the structure of how it's being set up, of like how people are thinking about it and how people are kind of designing these models. So cascade diffusion. So as I mentioned, those images, the kind of naive diffusion model, it doesn't really work very well because you have to have all of those super kind of noisy images all next to each other. And those images, I mean, even regular images are very, very large, and these have to be vectors. So the amount of space that you need to store all of that images and to train all of those neural networks just becomes very, very cumbersome, and it takes up all of the compute resources very much unnecessarily. So how do we produce high quality images with this? Because obviously we could train, like an image of a 4x4 square very, very easily with this technique. But how do we produce these high quality large images, the kinds that we want? There are two main techniques that have emerged: cascade diffusion and latent diffusion. So cascade diffusion is used by Google's Imagen network, which is still under work by Google to this very day. And basically, it involves taking the class conditionals, essentially the conditioners, the language vector that's being fed into the neural network, and conditioning it to produce a specific type of result. And we produce a very, very small image, and then we use a modified super resolution network essentially to expand that image. So we operate on denoising a very, very small image, and then we expand the resolution with each diffusion effort until we have a large enough image. And so obviously that technique has managed to work very well for Imagen, but for the rest of us, there is another technique that was used to create the open source stable diffusion model that we are focusing on, and that is latent diffusion. So if you remember when I discussed the variational autoencoders that essentially crush down the images into a much more a much smaller space, essentially. So what we can do is we can actually take those variational autoencoders and we can crush down the image, and then we can run the diffusing process completely in the latent space of that crushed down representation of the image. So essentially, we crush down all of the images in our training set, and then we run this diffusion on them, and we learn how to diffuse the images, and then we take the results, the outputs of that, and we decode them with the same autoencoder, with the other half of the autoencoder, rather. So instead of operating on this very large kind of space, these large images which have lots of entropy, lots of blank spaces that don't really matter to the output, we're operating exclusively on a very crushed down, kind of close to the semantics representation of the images. Is my mic not working? Oh dear. Well, at any rate, I guess I will be carrying this around. But this kind of compression is motivated by an effort to improve the semantic power of the model, in addition to its kind of its computational tractability. Obviously, you can see on this graph the semantic compression. The kind of what we want is to kind of for the neural network to map to kind of semantic things that are like in reality, like a hand or like a camera or like a dog. We want it to map to these sorts of concepts rather than to just map to pixels and which pixels tend to be next to one another, because that sort of thing obviously isn't as interesting. So you can see here this graph represents the perceptual compression, which is just kind of tiny little fiddling with the bits, versus the kind of real semantic compression that kind of completely twists everything around. So let's just quickly review what I was just discussing with how we would build this sort of model from scratch. Obviously, that would be cost prohibitive. Even Stable Diffusion, which is one of the cheapest of the models as far as the amount of money it took to train, cost apparently around $600,000 in computation. So unfortunately, it can't exactly be trained on our home desktops. But from a purely learning standpoint, let's go through how we would train it. So the components for latent diffusion are the variational autoencoder to crush the data down and operate it on it, and then build it back up again. And then there is the UNet or another architecture, but usually it's a UNet neural network to basically operate on each image and return the denoised or diffused kind of output image. And then there is the text encoder to turn the natural language into vectors, which we then condition the neural network on. And obviously the data, huge amount of natural images with their associated labels. The UNet neural network, I'm sure some people are familiar with this, but essentially it takes an image and it operates on that image in order to kind of train on how to modify each of the pixels based on all of the other pixels, based on how everything is structured in the image. Most importantly, as far as diffusion models go, the reason why this is so critical and so common is because it's a convolutional neural network. It's a CNN. So the dimensionality of the output and the dimensionality of the input are going to remain the same, essentially. And we don't need to have kind of a fixed size necessarily for everything. All right, so in our imaginary example, first we take the autoencoder and the text encoder, and we run them on every single image and on every single label. So all of what we have now would be a crushed down representation of all of the images and a crushed down representation of all of the text. And these are going to be the actual inputs that we are going to use to generate to run the training. But on the compressed versions of the outputs, what we do is we add noise. And remember, we're adding this noise in compression space rather than in pixel space. So we're creating a series of successively noisier versions of this. And now we have pairs between each given input of compressed image and each slightly less noisy output of that compressed image. And we've produced thousands and thousands and thousands and thousands of these pairs, and now we can train on them. And so we train our networks on each level of the noisy and compressed image to the next least noisy or less noisy and less compressed version of that image, alongside the vector output of the text encoder and the random seed. So these are kind of all designed to output that compressed image in latent space. So this is all occurring inside the, in essentially the dimensions and the structure of the kind of middle aspect of a variational autoencoder. And so once we have trained our model on all of these pairs of data, inference is relatively simple. We take as input a piece of natural language, just like a dog in a house or something, and we run it through the text encoder to get a vector, and then we take an image of kind of random latent space noise from the autoencoder. So an image of completely random noise, and then we run them through the model, and with the language vector and the associated random seed, and we run this model over and over and over again several times. So 10 or 20 times is pretty common with Stable Diffusion in order to get the output, I believe. And so what's going on here is that each individual step is removing a small amount of ambiguity or noise from the original the original kind of pure noise, pure entropy example. So it's kind of, it's slowly transforming it from a completely noisy kind of essentially blank slate of static into an actual image of what we desire, using the language vector to condition it at each and every step and to kind of mold it back into what it ought to be. So once we've repeated that process enough, the output of the model is all in latent space, remember. So all we have to do to get the actual pixel space version of it, to get the original image, or to get the image that we want from that piece of text, is that we take the decoder and we decode the image. Remember, the decoder is the other half of the variational autoencoder. And so, so other diffusion networks we're not going to touch on too much, but Imagen is one by Google that, as I mentioned, is a cascade diffusion model. Has been very, I mean, Google is funding it, obviously, so it's been getting a lot of work and a lot of money poured into it in that sense. DALL-E 2, in many ways, kicked off this whole kind of craze of the generative image models, and Midjourney is another interesting model. I believe that DALL-E 2 is also a cascade diffusion, and that Midjourney is latent diffusion, but I am not certain about that. Let's move on, though, from how these models are trained and their structure to the techniques that have kind of grown up around them, and the cool and interesting things that we can actually do with these models once we have them. Obviously, we can just take a piece of text like a dog lived in a house, or a large barrel or something like that, and we can just generate an image from it, which is very cool. But there's even more that we can do. We can go from image to image, moving around the search space, in painting, out painting, tiling images, negative prompts, and I will go through all of these techniques. First, though, one of the best ways to experiment with this is Automatic 1111's web UI, which allows you to work with the latest, well, not the latest actually, but the next close to latest Stable Diffusion model, as well as all of these kind of complicated techniques, different sampling methods, all sorts of really useful stuff. This is a drawing that I made, not Stable Diffusion, but I will discuss that in a moment. So remember when I said that we gave Stable Diffusion a completely noisy image as an input? So what if instead of a noisy image, we gave it a complete image, essentially. What if we gave it an image that already had stuff on it, and then we used and we gave it to it essentially in the midpoint with a little bit of noise on it, so that it would kind of slowly bring the image back to us, but it would start out at our very specific image that we already wanted. So this is a really, really powerful technique that we can use to take an existing image and essentially use it to kind of enforce the composition or the style that we want in our resulting image, and have a lot more control over it. So as you can see, this is what Stable Diffusion produces from the image on the previous slide, which is very artistic, in my opinion, kind of an artistic interpretation. And so this kind of process allows you to really guide the diffusion and produce an image that is much more in line with what you were thinking in many ways. This is another image that I drew. So this allows for a lot more control over the results. You can kind of enforce what will be, what the results will be much better. And this, I like this one in particular, but this is kind of the Stable Diffusion result of the previous slide. It's kind of a cool little Sumier effect. As you can see, because Stable Diffusion is operating on kind of the pixels and the kind of general setup of the image, because there are so many steps that it's going through, often it is not operating on as much the kind of the styles of the image aren't carrying through. So this kind of enforces a much more kind of a composition from the user and a style from Stable Diffusion. So negative prompts are another really interesting thing. So since the language that we're inputting is a vector, we can also use that to kind of steer it away from other vectors. So we can use that to kind of essentially steer the conditioned results to be as far away from a certain vector while still being close to another vector that we have selected. So as you can see right here, we can use, this is an example from the WebUI wiki. So if this image, I'm not certain exactly what the prompt was that produced it, but this is it with no negative prompts. And then with the negative prompt of fog, you can see the kind of fogginess of the original image clears away. And then with fog, grainy, and purple, it completely removes the purple from the previous image. So the negative prompts are also a really powerful way to kind of steer yourself away from certain things or towards certain things if you know exactly how you want to kind of push it, essentially. So tiling images. So tiling kind of and arranging images is often really cool, in my opinion. Kind of those beautiful, mosaics and stuff. And so using Stable Diffusion, by predicting kind of the edges of particular images, we can create kind of images that are automatically designed to tile in a much more interesting way. There's a little GitHub that that can create these kinds of things using a slightly modified version of Stable Diffusion. And another property of kind of vector inputs and numeric sort of inputs is that we have a search space. Essentially, we can move, we can adjust a given kind of variable over the course of several kind of options, and then over the course of several more options, we can compare them kind of all right next to each other. So this is really useful if you're creating an image and you kind of like it, but you want to modify some small part or some small aspect of it. This kind of search space, which you can do with the WebUI, the automatic 1111's WebUI, is you can create this kind of search space and you can see kind of very physically where everything else is, like how each modification would perform on that individual image. So in painting, is also a really useful technique that has been long in discussion and has been kind of the subject of a lot of research and analysis in computer vision for a very, very long time. So obviously, if you take a picture of something and someone runs through your image, there's no real way to kind of magically get the image from behind it, because if they ran in front of something that is important, you have no way of knowing what that thing was. So in painting is kind of the attempt to create programs that can predict what would be behind something if it wasn't there in the photograph, and then removing that object and replacing it. Obviously, Stable Diffusion is not perfect, since you can see clearly the lines between what was in painted and what wasn't. But it's really a major step forward in the construction and the kind of physical creation of what's behind these images, because you'll see the kind of area in other in-painting programs. It's very, very difficult to create kind of the area or what was literally behind something, because you don't know. But with Stable Diffusion, you can actually create kind of that object and make it realistic and make it look real, even though it is completely obscured in the photo by the dog. So outpainting is not as useful in kind of, I guess, everyday, normal, boring life, but it is very cool looking. And outpainting is where, if you have a kind of smaller image or an image focused on something smaller, what if that was only a zoomed in piece of a larger image? And so, as you can see here, you can produce kind of all of the surroundings of a particular image and make it seamless and make it blend in, which is really, really cool. So now that we've learned about the current techniques that are most popular and kind of in widespread use at the moment, let's look at the future possibilities that are just in their infancy, including AI for video, which is basically taking this same kind of principle and using it to generate videos instead of images, which is already in development and in some sense. AI for music and audio and sound, which is also quite in development. Developing 3D models for 3D meshes, essentially, for games and for all sorts of cool stuff like that. And sketch simplification, which is very near and dear to my heart as someone who, as you can see, makes a lot of sketches. Sketch simplification is basically the kind of using computer vision to create a kind of line art from sketches. So turning a sketch into a finished kind of product, basically. So AI for video synthesis. So Meta and Google have both produced models that do something kind of similar to Stable Diffusion for video as opposed to text, but the results are not as impressive as Stable Diffusion for many people yet. Video, obviously, the human eye is kind of primed on video, essentially. I mean, we're watching, real life as though it were a video in some sense. So it's very easy for us to detect kind of things that break the physical laws of the world. When someone reaches down to grab an object and their hand melts into the object, it's very obvious that that is kind of not a real video. So it doesn't really have the forgery in a sense that Stable Diffusion can do, in a sense that it can't really replicate what human artists or human videographers can do. Another unfortunate thing is that a lot of these models are not open source, so people can't really experiment on them and generate new and exciting and more interesting models. But if you are curious, Imogen Video, they released a paper just a couple weeks ago, and I assume that they are interested in releasing more over the next few months and weeks and such. So that is something to keep one's eye on. AI for music synthesis. So music and audio are another really interesting subject because in many ways, music is kind of just a one-dimensional single dimensional sort of image. And so it really should suit this kind of diffusive model very, very well. There's also a huge dearth of labeled audio all over the internet that's very well available to a lot of researchers. But unfortunately, the results have not been too impressive relative to that for a number of reasons. A lot of sound isn't as well labeled as sort of as images are. Like, two pieces of music might be labeled jazz that are completely different in the same way that two pictures that are labeled dog are not. So unfortunately, that hasn't completely materialized, but this is a really important space to watch out for. In particular, voice synthesis. If you go on YouTube, for example, there are people who use AI to simulate like the voices of Biggie and Tupac reading the Declaration of Independence and silly stuff like that. But this is really kind of a brand new technique that is taking the audio neural network space by storm. I forgot to mention, Mulan is a really interesting attempt at this sort of thing with the embedding of music and natural language audio. And Diffwave is another kind of attempt that you can read about if you are so inclined. So AI for 3D modeling. This is really kind of accelerating very quickly and will probably make its way into some indie games near you at some point in time. But Diffusion is the name of the kind of setup that a lot of people are interested in, because Diffusion is actually really interesting. It's not its own trained model that's trained to go from labels to 3D meshes, the same way that, Stable Diffusion goes from labels to images. Instead, it actually takes Stable Diffusion, or in their case, Imagen, and it creates an image, and then it uses something called NERFs, or neural radiance fields, to generate the 3D model straight from the image. So there's actually an open source implementation called Stable Diffusion, I believe, on GitHub that actually is doing this. Unfortunately, these results are from the scientific paper created by Google at Imagen. So unfortunately, this kind of version of the model can't really be used because obviously Imagen is proprietary. But the Stable Diffusion version on GitHub is available. So that's really cool. Finally, before we finish up, and I show you guys just a very quick way to use this in your own programs if you are so inclined. Let's go into some of the ethical dilemmas that have emerged from this from this space just recently, including the use of an artist's real name in the prompts and training, even if they disapprove, and the kind of more general philosophical dilemma that many people are expressing, that it takes away something from the general humanity. So first, use of an artist's real name. So I didn't touch on this too much, but when you're writing prompts for AI art and for Stable Diffusion, one of the best ways to get a good result is to type in created by blah, 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 like created by Leonardo da Vinci or created by Abraham Lincoln. If you type in someone's name, especially a specific artist's name, you can often get a much better result and a much kind of cooler looking image that really looks like a cool kind of artwork. But the problem is a lot of the people whose names are being written down in this way are not big approvers of this sort of technique. In particular, a popular kind of video game artist named Greg Rutkowski. Is very common to be used in kind of these AI art prompts, but the results he disputes vehemently on an ethical basis. And it kind of raises an interesting ethical question, because obviously if a real artist just got inspired by Greg Rutkowski and created his own, painting based on that, but obviously completely different from anything he had literally created, I mean, wouldn't that be legitimate in a sense? But then there's the other flip side of that, in that the AI obviously is trained in a way that a human really can't. So it's kind of comparing apples to oranges. So that's an interesting dilemma. And then there's also the kind of broader philosophical dilemma that many people have raised. A lot of philosophers from Nietzsche to Schopenhauer and more have kind of reflected on art as the highest sort of stage of what people can do. Nietzsche in particular was very interested in the contrast between the Apollonian or kind of logical and rational center of people and the Dionysian or kind of artistic and wild sense of people, with the Apollonian and Dionysian being in constant conflict. But if the Apollonian has kind of managed to artificially generate the Dionysian, that raises kind of the broader dilemma of what the Dionysian is even doing, in a sense, which is kind of interesting in many ways, in my opinion. And as far as solutions to the ethical dilemmas, obviously there's no real solution to the existential ennui of what people's purpose in life is. But there is a solution, in my opinion, to the use of people's real names. And I prefer, in general, to use the names of long dead or public domain artists like Caspar David Friedrich, who cannot tell us that he dislikes AI art. So that is my setup. Now, let's go into how you guys can use this on your own, if you so choose. We are going to set up a simple script. I'm going to show you a couple methods, and then we're going to use my API token to get it to produce a little image from a prompt. So what we're going to do is basically we're going to contact the Replicate API that is running this model, on their own computers with, huge GPUs, instead, so that we don't have to download a 4 GB file and run it on this laptop, which is, dinky. So let me see. So, all right, 3 quick methods. So method 1. This is kind of the fastest method that is available. It only works with Python. It's just kind of a very quick method to get a result that's good for kind of showing. We can just export this Replicate API token as our token. I'll show you my token in a second, and obviously I'll disable it after the talk, just as a demonstration. And then we just install Replicate. Import replicate model equals replicate.models.get, and then the output is models.predict. So this is just very simple stuff. So the advantages obviously are that it's simple and easy, only a few lines of code, no hardware requirement. Again, it gets sent to their servers. Then the disadvantages obviously are that it requires an API token. It's Python only, and it doesn't allow a lot of the more advanced usages. Method 2, to manually access the API. I like doing this. I created a little gist in case anyone is interested. I'll put that more on screen later after I've shown everyone the API token and everything. And so this has the advantages that there are still no hardware requirements. Obviously, it's just pinging the same thing that the library is pinging. The disadvantages being that it still requires an API token and a small amount of money, although it's only like a penny. And obviously I'm paying for this one. And it still doesn't allow some of the more advanced usages. Method 3 is the exciting method. This is for running if you have a ton of GPUs. This doesn't work for my laptop, unfortunately, but it works on my desktop at home. You can find this on the replicate.ai website. They have this exact kind of Docker prompt available. Basically, you just run kind of the mini Docker version of their servers and then ping it with the prompt and the width and the height and yada, yada, yada. All right. So now, let's head out. And then we will generate a little bit of our token. So where's my token? Token. I'm going to put it. API token. Huh. I guess I put it. Pardon me. All right, I left it on the website. Diffusion. So this is the website that I mentioned. And here is the API token. I will copy it into the YouTube chat so that anyone can grab it. And obviously I'll disable that after the talk, but it's free to use until then. So in order to use this token, we take it in here. And now I'd like to open it up to the members of the audience to give me a prompt for something to generate with an image. Any ideas? Doesn't have to be serious. Just one word. All right. We'll do pumpkin 4K created by Caspar David Friedrich. How about that? All right. And here we go. Ta-da! What'd I tell you? Sure thing. I thought he was obsessed with chimps. Same time. Here we go. Good stuff. Ah, dang it. Close. No cigar. Already done. All right. So, good stuff. That is essentially my presentation. I have the credits right here with a lot of the articles and sites that have more of the mathematics and more in-depth explanations of what I've been showing here. But yeah, any questions?
So with all these other inference methods like etc., how are those achieved? Do they use like a fine-tuning process like transformers to like slice up layer off, or do they do something completely different?
Well, it depends. So for this, we're talking about the. Let me see. Hold on. these techniques, the notable techniques. So some of them, so the negative prompts, that uses, I believe, just a special little inference on the text. So essentially it kind of takes the text vector and moves it as far away from the kind of negative prompt as it is to get a new vector that it then inputs into the thing. I forgot to mention, but the text encoder used by Stable Diffusion is OpenAI's clip encoder. So that is how they get the negative prompts. For image to image, actually, it's basically part of the structure of the item. So essentially, all you have to do is just take the regular network and give it kind of an image and add a little bit of noise to it, and it will kind of do that on its own. So there's no real kind of special modification for the image to image. For moving around the search space, I mean, that's kind of just the way that it is designed naturally. And for in-painting and out-painting, I mean, it just, again, it's very close to the kind of the structure of the output. With in-painting and out-painting, what it actually does is that it runs the diffusion process, and then it copies over the new, like whatever was newly created with the original, with like the part of the image that you want to keep. So basically, it kind of, at each step, it adds the original image back in order to kind of redevelop it. For tiling images, that is a specially trained one. The guy on GitHub kind of specially trained his to kind of create more tiling experiences. And for outpainting, that's kind of just the same as in painting. Yeah. Yeah. Most of these techniques are messing around with the model. There are actually a number of kind of specially trained image to image, or not image to image, but specially trained versions of Stable Diffusion floating around on the internet right now. Because the web UI actually allows you to train your own if you like to train an addition onto it. If you have, you know, a good GPU. But yeah, most of these right here are kind of just playing around with the way that the model is structured. Anyone else? One sec. Yeah, I mean, I was just doing that really inefficiently because it was the way that I set it up. So I like, because I don't always work in Python, especially for my little, I actually created a little app, sobelstoryboard.com, that kind of uses Stable Diffusion in some way. And on the app, in the Lambda functions, I use JavaScript. So I didn't want to, so basically I'm very used to using the API. So this is the kind of method 2 that I was mentioning in the slideshow. So I'm literally just pinging like an HTTP output. And then I created this, but for some reason, whenever I run this function, like just the test underscore stable underscore diffusion, it doesn't work in the interactive prompt. So I just copied and pasted a bunch of lines. So that's just me being super inefficient in order to get it to kind of run and display super fast.
It works.
I know. I would suspect that they're just playing around with the model. I mean, for example, if I rerun this exact same prompt, because we didn't give it a specific random seed, it will generate something pretty different. I would suspect. Yeah. See. See, there we go. A little late, but there we go. So as you can see, it generates very, very different responses every single time because there's that random seed and because it's kind of operating on such a broad image space. Like I would suspect if there's an image with a lot of different kind of things, it's that it's the result of kind of just rerunning the same thing with just the random seed changing. But I mean, I wouldn't know unless I saw exactly what they were doing.
He's talking about is called Dream Booth. It's a project that researchers at Google, they fine-tune Stable Diffusion to detect a subject in the image and then keep the information related to that subject and then change everything else about the image so you can, do whatever you just said.
Yeah, kind of like the in painting. Any other questions? Any other prompts? All right, then I guess we'll have to end there and enjoy the pizza.